It's too much information.
I'm going to share what I understood.
Yeah.
I'm sure I'm wrong.
But imagine the coin in flight. And let's say you capture it in a box as it is in flight. That's a quantum state. So I should tell you that I was one of those people in 2000 who actually did not write the JEE exam.
Okay.
So, I have never thought about this as, is there a, career path here? It's more about what has interested me. Last year with Google's 100 qubit experiment, it has more or less come. That's like a first proof of principle that you can put 100 qubits on a chip. You can connect them all up in some way that makes them resilient to this error. Take your friend's notes, right, the night before the exam and make a copy of the entire notebook. No, not possible. So you cannot copy quantum information.
Hi, this is Amrit. We are at IIT Madras, my alma mater, and India's top university for people who like to build. We are here to meet some builders, ask them, what are you building? What does it take to build? And what makes IIT Madras the best place to build?
Hello and welcome to the Best Place to Build podcast. Today we are sitting with Professor Prabha Mandayam, a renowned physicist and a faculty here at the Physics Department at IIT Madras. Her area of interest is quantum information and error correction. She's an author of a book, Functional Analysis of Quantum Information Theory, and her NPTEL lectures on quantum computing are very popular. You can see I'm looking into my notes, so I know nothing about this subject. So it's an opportunity for me to learn. Welcome to the podcast, Professor.
Thank you, Amrit. Thank you for having me here.
Professor, I don't know anything about this, so it's a challenge I'm offering to you. Please, can you tell me about quantum computing in the next half an hour so that I can survive the next 10 years?
Yes, certainly I will try. So, okay, so quantum computing, as the name suggests, is that you try to compute with objects, physical objects that are truly quantum in nature. Right. So a very simple example that or a simple picture that I can give you is a kind of geometric picture to contrast how a quantum bit will be different from a classical bit, right? So in classical computers, you know that we encode in zeros and ones, right?
Correct.
Classical communication is zeros and ones, right? Yeah.
Yeah. So in what I know of classical computers is that we convert everything to binary. There are a set of binary operations. There are a set of algorithms that work on those binary operations.
Yeah.
At the same time, on the physical side, there's this thing called a transistor,
right,
which mimics a bit, a 0-1 state.
Right.
So we build a physical hardware based on transistors, which can do these computes.
Absolutely. So now, instead of this humble 0-1, you imagine now a sphere, a ball, and then you put the 0 and 1 at the two poles of the sphere. So 0 could be at the north pole, 1 could be at the south pole, right? But now, instead of just having these 2 points in which you can transcribe information, you now have all the points on the surface of the sphere.
Okay.
So that's what quantum does, right? If you, instead of encoding into these zeros and ones, if you encode into a quantum state, then that means that you somehow have access to the entire surface of the sphere and not just 2 points on the surface of the sphere. So you can imagine that the space that you have to now read in, put in information has exploded because you've gone from just 2 points to an infinity of points on the surface of the sphere. And the way this happens is through this magical word called superposition.
Okay. So far I've understood that I can imagine a sphere which rotates, and any position of that would be a number between 0 and 1. Which is the infinite number of numbers.
Correct. So rather than think of it as a number between 0 and 1, you should actually think of it as, don't think of the sphere as moving or anything, just think of a static sphere.
Okay.
So how do I identify any point on the surface of the sphere? I need 2 angles, right? I need a latitude and a longitude, like the surface of the earth. To identify any point on the surface of the earth, I need a latitude, which is the angle with like one axis, and then the longitude, which is like you kind of project onto the equatorial plane, and then you have the longitude, right? So now, these are 2 numbers, 2 angles, right? And these angles go between like 0 to 180, 0 to 360, right? So with these 2 angles, you can identify this infinity of points.
Okay.
And so a quantum state is that. It basically is like identifying a point on the surface of the sphere. where one point corresponds to your classical bit 0, the other point corresponds to classical bit 1, but now you have all these different possibilities in between. And that's what superposition does for you. It allows you the ability to be somewhere in between a 0 and a 1 state.
Okay.
I can think of 0 as an off state and 1 as an on state, right? And quantum allows for the possibility that you could be in either the on state with some probability or the off state with some probability. The other way to think about it is a coin toss, where your coin, imagine it's in flight
Right.
as you're tossing it. But once it is tossed, it's either head or tail. There's nothing in between. But imagine the coin in flight, and let's say you capture it in a box as it is in flight. That's a quantum state in a very, very loose sense. I mean, I'm not being very
Fair enough. So
precise.
if I take a high speed photo at any point, then it will be at some point.
Yeah. So you can imagine that if it's like I tossed, but I kind of, toss it and put it in a box.
Okay.
So now I don't know whether it's going to land head or tail,
Okay.
and it's not a fair coin. Okay. It's a biased coin, which means there is some non-trivial probability of landing head and non-trivial probability of landing tail, not a 50%.
Okay.
50% would be one such state,
Option.
one option. But so now you have all these possible states with all these different possibilities, probabilities for head and tail.
Okay. So this is a qubit.
This is a qubit, a
Okay.
quantum bit. And now you imagine computing with these quantum bits, right? So now a task that I do on a classical computer, I have to encode in either 0 or 1 or in some string of zeros and ones.
Right.
But now I have the option of encoding in these in-between states. Okay. So imagine a simple task. I give you a binary function. Okay. And I say, is this function constant or balanced? Okay. I'm getting a little bit technical here. Constant meaning f of the function value for bit 0 is the same as the function value for bit 1. Balanced means the function value for bit 0 is different from the function value for bit 1.
Okay.
Now you have to tell me, is the function constant or balanced? And I first give you a classical calculator. So you punch in 0 and you find out what the answer is. You punch in 1, you find out what the answer is. So you have to query this, you have to kind of use this classical box twice. But in place of that, if I give you a quantum box, I give you a quantum processor, and I give you the ability to prepare these in-between quantum states. Now you can input a state which is a superposition of 0 and 1.
Okay.
And in a way, your box can simultaneously compute both values at the same time. Okay?
So if I imagine this function as a box in my classical computer, I would have to use the box twice.
Twice.
And in quantum computer, I use it
once. And this is for a single bit. Right? So this kind of model in computer science parlance is what's called oracle-based model. The box is like an oracle, like this Greek goddess who knew all the answers. And but you have only one shot with her. Like you can only ask her one question. Or the number of questions you can ask her is very limited. Now the quantum box gives you an advantage. Because you can, with a single query to this oracle, and the output, you can actually know whether f of 0 is the same as f of 1 or f of 0 is different from. But this is a toy problem. Now you imagine scaling this up. So for example, instead of a single bit function, you imagine an n-bit function.
Yeah.
Turns out that this speed up is actually exponential.
Okay.
Meaning classically, I would need an exponential number of trials with this box and write down all the answers. And then I can decide whether the function is constant or balanced. But with a quantum box, I can again do it in a single query. Because it doesn't matter how many states I have, I can make superpositions of all of these.
You're using the word superposition?
Superposition, as in to say a combination of two different classical states.
So in a very like 12th standard math level, it's like evaluating a function for different values at the same time.
In one way, if you want to think about it, think about a vector. In math, we do this coordinate geometry and you have vectors. Now you have a unit vector along x, you have a unit vector along y, but then you have all these vectors in between, which you can break down as some projection along x and some projection along y. So, the exact analogy of this is a qubit which you can prepare using polarization states of light. Right? So you think about your Polaroid glasses, what do? They basically filter out different polarizations of light, right? Now you can have light which is polarized along this direction, light which is polarized along this direction, but you can also have 45-degree polarized light. You can have 30-degree polarized light. You can have 20-degree. All these are valid states of light, okay? Now having only horizontal and vertical is like having only bit 0 and bit 1. But now 45-degree polarized light is a cos 45 combination of horizontal plus a sin 45 combination of vertical. That's exactly what superposition is. It's like having a vector in a three-dimensional space, right? So in fact, we say quantum states live inside what are called vector spaces mathematically.
Okay.
So
before you proceed on that,
yeah,
I want to ask you a question here which comes to my mind. So far, I'm not clear why it's called quantum computer. Where did the word quantum come from?
Right. So now this polarization that I spoke about, right? The light that's coming out of this, for example, is not polarized. But now I can imagine putting a big filter or sunlight, right? We use your Polaroid glass. But now there are tens of thousands of photons or millions of photons in this sunlight that is coming to us, right? When you have these many sort of particles or a collection of particles, right? Then you're really not in a quantum state. You are in what we call a classical state of some sort. But now, if you use certain filters and so on, and you reduce the number of photons so that you're down to a single photon level. The same analogy that I told you, right? Now, what does your Polaroid glass do? It blocks a certain fraction of light.
Yeah.
So there's a certain fraction that goes through and a certain fraction that is blocked. And that's why you feel better wearing Polaroid glasses in hot sun. Now, if you had a single photon instead of this beam of light, what will that single photon do? Will it get blocked or will it go through? Now, a photon cannot split.
Right.
So you can't have this possibility that some fraction will go through and some other. So now you're really in this single quantum level. And now, how do you describe the state of that photon? That is what I call as superposition.
Okay.
Because at a bulk level, I can still talk in terms of intensity of light and more classical notions like that. But when I'm down to a single photon level, that is when I'm truly probing the probabilistic nature of these single level particles, right? So the theory that governs these microscopic particles or microscopic objects, like an electron spin, a single electron, the spin of a single electron, the polarization of a single photon, a single atom, right? The laws that govern this are the laws of quantum mechanics. And since you're using these laws of quantum mechanics to now you treat these objects as information processing objects, you call this as quantum information theory or quantum computing. You call the kind of bit that you get out of this as a quantum bit, right? It is one that follows the laws of quantum physics as opposed to Newtonian laws, which are, classical. Yeah.
Quantum mechanics as a field is quite new itself, right? Like it may be 50 years old or something like that.
We are celebrating 100 years of quantum this year.
Is it?
Yeah.
Okay.
So we are celebrating 100 years of quantum science and technology, quantum mechanics this year.
Can I just say that implies that there must have been a starting point? What are you considering as?
Yeah, so this is hard to say, in fact, yeah. So what they're considering, so why 100? Because in 1925 was when this Austrian physicist by name Schrödinger wrote down this famous equation, the Schrödinger equation, which governs how quantum particles behave, the dynamics, both the statics and the dynamics of quantum systems. Right?
I remember the Schrödinger equation from my first year. I think it's also taught in class 12 sometimes.
Yes. Stuff
of nightmares for me. I'm sorry. But you're saying that from Schrödinger's description of quantum physics, the field evolved and at some point, okay, separately you're saying that those laws can define what is superposition.
Right. So the ideas of superposition, the idea of this being a probabilistic theory, the idea of uncertainty principle, for example, all of this goes back to 100 years, right? So, for example, Heisenberg also formulated his uncertainty principle, which also is something that we all learn in school and maybe first year physics courses. That's also 100 years old now, right? So, the development of the field happened sometime between 1920 to 1925. I would say those were the golden years. The field itself actually goes back, according to me, to 1900s at least, when the photoelectric effect was first discovered, which is when you were literally probing this, single particle kind of interaction. You had an electron.
The slit experiments.
The double slit, yes, but no, this is when you shine light and you release a single electron out, right? And this is what then led Einstein to formulate the idea of photon, that light the energy levels of light exist in these integer numbers of a basic quantity, and that basic energy quantity is what we call a photon. Right? And then you have like integer number of photons and so on, right? So this quantization of light, right, happened in 1905, right? That's when Einstein came up with this theory of photoelectric effect. The idea of h nu, the energy being of a single photon being h nu and all that, right?
Can I just summarize so far? You've explained to me what is a qubit. You've explained to me what is superposition. And then we are having this conversation of why it's called quantum, because it came from quantum mechanics.
Yeah.
The starting point is nominally, like, you have to decide some starting point. So it's the
Schrodinger equation, then it's 100 years. Yeah,
Great.
It's 100 years of Schrodinger equation. I just want to say that the idea of quantum computing is about 40 years old now.
Okay.
So it was in the 1980s. Is a physicist in Oxford by name David Deutsch. So the problem that I explained to you of this identifying whether a function is constant or balanced, this is called a Deutsch problem. So he was the one who came up with this toy problem, where you could then show that using quantum mechanics, you actually achieve a speed up over what you can do classically. And this little algorithm sort of way of doing it is what's called Deutsch algorithm. So it's the first quantum algorithm, which
to go from these really complicated papers that Schrodinger, Einstein, Heisenberg are writing to something that all of us should care about, the step there you are saying is important, is the fact that it can compute much faster than a classic computer.
Exactly.
So that is why we should care about it.
Exactly. Absolutely. Yeah. So the problem that I mentioned is a toy problem, but sometime in the 90s, early 90s, a mathematician by name Peter Shor at MIT showed that you can identify the prime factors of a number exponentially faster than the best classical algorithm to date, the best classical algorithm, if you had a quantum computer. So he came up with a quantum algorithm that can factor numbers exponentially faster. And this made everybody sit up and take notice. Deutsch's work was not really noticed because that was a toy problem. Okay, that's a cute thing, but who cares about the toy problem? But factoring, because by then everyone knew that what is at the heart of all secure communications today is a protocol by name RSA, which relies on the computational hardness of prime factorization.
Okay.
So I give you a very large number, let's say even a 20-bit number, let's say. And I say, can you find the prime factors of this? I even tell you that there are exactly 2 prime factors for this number. Okay. But it's very hard task classically. The best, so, classically we classify problems as being either NP or P. Can you solve them in polynomial time? Or can you only verify them in polynomial time? So you don't have an algorithm that solves in polynomial time. That's NP, right? So factoring is so far believed to be in NP. It's not that anybody has proven it, but the prime factorization problem is believed to be in NP. And in 1992 or 3, I have to check, maybe you can show your viewers the correct year. Peter Shor came up with a quantum algorithm that can factor numbers in polynomial time. If you had access to a quantum computer, which can encode information in quantum bits, you do quantum gates, quantum logic gates, just like how you do classical logic, run a quantum algorithm, then you can do this exponentially faster. So then,
okay, so but this is still an algorithm. This is an algorithm that says that if we have these quantum states, and then we could write math in such a way that factorization would go from an NP hard problem to a very simple.
Right. It's not known if it's NP hard. In fact, it is not NP hard, it's NP. NP hard is technically
I'm so sorry.
different from the NP.
It goes from an NP problem to a P problem.
Yeah.
Okay. Yeah. And you're saying that this is something that made everyone sit up because factorization as a problem, or the complexity of factorization as a problem, is the basis of RSA algorithm.
Yeah.
maybe other algorithms
Yes.
which are used in encryption
Yes.
like every day.
Every day. Yeah. Public key encryption. Right. Your ability to send emails over Gmail and be guaranteed that others are not reading it.
So if I had a quantum computer and nobody else had a quantum computer, then I could technically
crack all this. Yeah.
I could crack the RSA algorithm.
Yes. Yes.
Daily encryption.
Yes.
Okay, that sounds really powerful.
Yes.
Okay.
Yeah. So all governments then got interested. The government funding started for this program. Then people started looking at, can we build this? Right. This is, like you said, a math result.
Yeah.
Now, can we actually build these things? Is it possible to actually build a quantum computer?
Correct. There has to be a transistor movement.
Right. Now, that happened sometime in the early 2000s with the advent of the superconducting qubit. Okay. And in fact, it was a group in Japan by Professor Nakamura that first started, in fact, demonstrated, I think, the first superconductor-based quantum bit. Okay. I must tell you, though, that there were folks at IBM, like Charlie Bennett and so on, who had demonstrated this polarization qubit that I spoke to you about. That's the easiest qubit to realize, right? Because that's just light. Now, you have to just bring it down all the way down to single photon levels. And then you can already start seeing these quantum stuff in action, right? You can start seeing superposition in action and so on. But that was not good enough to be able to do computing, okay, at that stage at least. But then the superconducting qubit showed that you can actually precisely control these single qubits. Now, the challenge, unlike in the classical case where you're still treating these systems as very macroscopic classical objects, here you're down to microscopic levels and you need precise control of these objects. And it's very easy to kind of, for them to move into the classical domain.
Which is 0, 1.
Which is 0, 1. This mechanism is what is called decoherence.
Okay.
Okay. And this is an important word because it then ties in with my research, which essentially is about how do you combat decoherence.
Okay.
Okay. This decoherence is what we call noise for qubits. And the key challenge till date is to be able to realize quantum bits which are not very susceptible to this decoherence. And even if they are, we have sort of error correcting codes that can somehow overcome this decoherence. So the challenge is to actually realize these error corrected qubits which can exist in their quantum state for long times. It's too much information.
I would share what I understood. I'm sure I'm wrong in some way, but let me just try. You're saying that in realizing a qubit, first of all, we should be able to give instruction to the qubit.
Yes.
And secondly, we should be able to measure and find out what state it is.
Absolutely.
In both giving instruction to the qubit and measuring, there's some error that comes in.
Yes. It's challenging to do it at a single qubit level to precisely control them. So what happens is that the quantum state is very fragile, the superposition state, right? You're precisely putting it at some point on the surface of the sphere, right? Remember. Now, it's very easy for this thing to simply collapse down.
Right.
Either to the equatorial plane or just go off to the North Pole, like the zero state, right? That's a very overpowering mechanism. So you're kind of trying to overcome that and precisely controlling this. One solution is, well, shut your qubit from all external influences, right? Make it so isolated that,
the electron or the photon or the microscopic element is moving because it's getting energy from everywhere.
Absolutely.
Right? So you're saying that if I shut out everywhere, then it will just sit and follow my instruction.
Absolutely. But then you have to interact with it so that you can make it follow your instructions. So now there's a trade-off. How much do you interact with it? And in that process, you're kind of opening up the qubit a little bit.
You're saying my interaction itself gives it the license to move.
Exactly.
Okay.
Yeah. So this problem is the problem of quantum error correction.
Okay. Wow, Professor. Just to get to what do you do, it takes me like 20 minutes to understand. Okay, but just since we have come till here, I understand from see, we now have a national quantum mission and all of that. I understand that we started this conversation on why it is important with respect to security and encryption and decryption. There must be more to it, right?
Yeah. So factoring was the first task, like I said, which made people sit up and take notice. Subsequently, another computer scientist by name Love Grover in Bell Labs, that's an Indian connection to quantum computing from the very beginning. So he showed that you can search over an unsorted database faster if you had a classic quantum computer. So this is called the quantum search algorithm. Now, this is an example of a useful task in a very application sense, right? So you can imagine now you have your route optimization problem, or you have a traveling salesman problem, so any problem which you can kind of model as searching over an unsorted database can be done much faster if you had a quantum computer. So classically, if you need n attempts or n steps to do this, quantumly you need only square root n steps. So as your n becomes larger and larger, you can imagine that you have a real advantage with a quantum computer. So these were the two main algorithms which brought in funding for quantum computing, both from government and from industry. Because the search is something that industry folks are then interested in. So both of these groups started building quantum hardware. So in one of the early groups in the US was at Yale, then at IBM. They started building quantum computers. But it wasn't until 2016 that they actually showed that you could put a certain number of quantum bits on a chip, right? Because now this polarization, qubit and all of that is like a tabletop experiment. It doesn't become a quantum processor. It doesn't become a computer. Now I need to have the ability to, how I etch transistors and this whole circuits on a chip, can I now make quantum circuits on a chip?
Fair enough. The breakthrough in transistor is actually photolithography, which allows us to sort of print transistors on a chip. So you're saying that that moment has it come?
It started in 2016, and I would say last year with Google's 100 qubit experiment, it has more or less come.
Okay.
Right? That's like the first proof of principle that you can put 100 qubits on a chip. You can connect them all up in some way that makes them resilient to this errors and this decoherence and all of that. So it was a very but it's still a proof of principle, right? We still haven't demonstrated Shor's algorithm on a quantum computer at a meaningful scale. I mean, we have shown that we can factor 15 into 3 and 5. We have shown that you can factor 21 into 3 and 7 and so on. But we haven't, so there are proof of principles like that. But can you really take like a 20-bit number and get the prime factors out? We have not yet seen that kind of a demonstration.
Walking back a bit, when you were talking about this realization in the beginning, you mentioned the word superconductivity.
Yeah.
Superconductive qubit.
Yeah.
And I sort of, broke you there.
Right.
Can you complete that flow? What is a superconductive qubit? And before that, there's a photon qubit. Is that it?
Right. So these are just two of them. So let me say that today there are at least 4-5 different architectures that people are simultaneously exploring to build quantum computers. The earliest one was the photonic qubit, which is basically the polarization states of light. The next one, which was reasonably successful and today which is the kind of the leading architecture, is the superconducting qubit, right? You basically take you etch a kind of superconducting material onto a chip, right? And you create this sort of presence or absence of a charge or presence of absence of magnetic field as a qubit. That becomes your 0 and 1. So what do you need for a qubit? You need to identify basically these two levels, the 0 and the 1, the on and the off level, like in a transistor and so on. But now you need to do it in a quantum way so that you can also prepare all these superposition states and not just have on and off, right? So the superconducting qubit relies on the principles of superconductivity, which says that your, for example, if you had a piece of superconducting metal, let's say, that means, so superconductor is what? It's basically you cool down certain metals at very low temperatures.
Yeah.
They offer almost no resistance to the flow of current, and this happens because these electrons, which are your charge carriers, they pair up into something called Cooper pairs. Okay. And now you can create islands or pockets here where you could either have a charge there or not have a charge there. That's a very crude description. But essentially, that's like your on and off.
Understood. I mean, I'm saying understood, but I should
yeah.
say acknowledged.
No, I'm also being very loose, in this, but I'm hoping that people will pick up some of these words and go look up
Yeah,
more.
go look up. Yeah.
Yeah.
At the very least, they can look up your NPTEL course.
Sure.
But
Absolutely.
tell me something now.
Yeah.
You said that the Google experiment last year had 100 qubits on a chip.
Yeah.
Um, but you also said that the quantum computing reduces the requirement of time, of polynomial time. So when we look at classical computing chips, they are in millions and billions of transistors.
That's right.
To have, how many qubits do we need on a chip? Is that a small number?
No, it does not scale. The number of qubits, you don't really get an advantage with the number of qubits in these tasks, right? What you get an advantage typically is with time, right? The number of steps that you need to do, right? Whether it's a number of, let's say, times you need to access this quantum box, or whether it's a number, the time to which, how deep are the circuits that you need to run in order to solve a particular problem, right?
Okay.
So if you had very sort of ideal qubits which are noiseless, then you could, for example, crack today's RSA with about tens of thousands of qubits.
Okay.
But the current benchmarks that I know is if you need to run these error correcting codes and do Shor's algorithm on error corrected qubits, then you need at least 1 million qubits. Okay, of the order of 1 million qubits.
Okay, so we are at 100.
We are at 100.
So there's a long distance to go.
Yeah.
Professor, now that I have understood this basic idea, and I can also appreciate why error correction becomes so critical. You're in the field of error correction. So can you give us an idea of what that looks like and just an overview?
Right. So now error correction is not something new to quantum. We do this in classical information theory all the time. I mean, Shannon's work is all coding theory. Shannon's kind of, in a way, gave rise to this idea of coding and so on. But classically, what happens, right? So I have my classical registers, my transistors and so on. I put in a 0, but then it somehow flips and becomes a 1, right? That's an error. That's what we call a bit flip, right? Now, classically, we say, oh, no, don't worry. Every time I want to put a 0, I'm going to put 3 zeros, or I'm going to put 5 zeros. And every time I put a 1, I'm going to put 3 ones or 5 ones. Now, the odds that all 3 are going to flip, or even 2 are going to flip, is much lower than the odds that only one of them will flip. Now, when I read out, I'll read out every set of 3 or every set of 5, right? And depending on whichever is majority, so if in a set of 3, I find 2 zeros and 1 1, I know that this was intended to be 3 zeros, but one of them flipped. So this is introducing redundancy.
Yeah.
And that's how you protect information. Now, in quantum, can you do the same thing? Yes and no. Yes, because 0 and 1 in quantum are like the classical 0 and 1. But now what happens when I prepare this 45-degree state? How does that get protected? Because now I'm not just protecting 0 and 1. I'm protecting what is called an entire vector space. I'm protecting all possible points on the surface of the sphere. So I have to protect superposition. Because that's the key resource for me now, right? So if I don't protect superposition, I'm back to classical. So to protect superposition, you can say, well, every time you have 45, you say 3 45s. But the problem is, in quantum computing or quantum information, there's a very basic no-go result called the no-cloning theorem, which says that you cannot make copies of arbitrary superposition quantum states. So you don't have a Guru Nath, which probably was there when you were a student here, where you have a Xerox machine and you take your friend's notes, right, the night before the exam and make a copy of the entire notebook. No, not possible. So you cannot copy quantum information.
But even in classical computing, there is a assembly code for take this value from here and put it there. It's a simple copy.
Right, but you cannot do that quantumly.
Okay.
So you can copy states which are like classical, which is your 0 and 1. But an arbitrary superposition, I don't have a universal Xerox machine that can copy quantum information. So this is what primarily makes quantum error correction challenging. So now you have to come up with clever ways of introducing redundancy. And here comes in another player in this whole game, which is entanglement.
Okay.
Which is a word which I have not used until now. So what is entanglement? Now, the idea is that you can have, now we're talking about single qubits. Now, I take this collection of 3 qubits. Okay. Now, I try to do an error correcting code on this, means I try to say, okay, every time I have a single 0, it's 3 zeros. Every time I have a single 1, it's 3 ones. But what about the 45-degree state? What I do now is I make a 45-degree state, not of 3 single qubits, but of this collection of 3 qubits, of this set of 3 qubits. Okay. So, it's like 3 qubits is 0 is my x-axis and 3 qubit 1 is my y-axis, and I've made now like a superposition of this 3 qubit 0 and the 3 qubit 1. But this is a state which I cannot break down into a state of the first qubit, a state of the second qubit, and a state of the third qubit. It's a state which cannot be broken down into its individual parts. The information is in the whole. So that's the idea of quantum entanglement, again, very, very naively. But this is the simplest, what I've explained to you is the simplest quantum error correcting code. It's called a 3-qubit repetition code. So you see, it borrows elements from classical, but then there's a quantum twist to it. And this circumvents this idea of no copying, because now what I do is I make a circuit. I make a circuit with 3 registers. The first register is the state that you want to encode. It could be any state.
Wait. You're using the word register. This is from the classical computing word.
Right.
Register.
Okay. Yeah. So qubit. So the first qubit. So when I say qubit or register, I kind of use them equivalently. A register is, I think of it as a single bit or a single qubit. So the single qubit is in some arbitrary point on the sphere. It's some arbitrary superposition. The other 2 qubits are in fixed states. And now by doing a circuit which involves some logical operations on all 3 qubits, at the output of this circuit, I have a 3-qubit state which can no longer be broken down into single qubit states, but which is successfully now protected.
The information.
Yeah.
So I want to say that when transistors were invented, and then the digital algorithms, the 0-1 algorithms got implemented into transistors, and that whole revolution took place between the 50s, 60s and 70s, and then suddenly it was apparent to the world that the world has changed. It's,
Right.
It's,
Yeah.
we are, we could go to the moon, we could build mobile phones, computers, all of that, right?
Yeah.
And so as you're saying it feels to me that we are at that 1950, 1960 level.
Absolutely.
And in the next 20 years or 30 years, as quantum computers get built, there'll be like will we all have quantum computers in our hand? Is that possible?
Yeah, my own, this is crystal ball gazing at this point, right? I mean, who knew in 1950 that, So there's this famous statement of Thomas J. Watson of IBM saying that perhaps the world has a need for 3 personal computers or 4 personal computers or something like that in the 1930s of, when we still had vacuum tubes and...
IBM thought of the computing revolution as something that governments and organizations will have.
Right. So today, I typically say this, that maybe we will have specialized quantum computing facilities, right? But then who knows, like I said, that's the way things are shaping up today. It seems to me that it is certainly, and this is already happening, but it is not happening at the scale where it can now start doing useful tasks. It's happening at a scale where you can do proof of principle, you can train people on it, you can teach them how to program a quantum computer, and so on and so forth. But it's not yet at a stage where hopefully we are cracking passwords and or even doing useful things like solving traveling salesmen or optimization problems and so on.
Maybe in future IIT Madras will have a facility and I'm a researcher and say protein folding.
Exactly.
I will here take this problem.
Absolutely.
And get a solution in 20 minutes.
Yeah. So you can imagine how IIT Madras had one of the earliest IBM computer stationed in India, I think, for that matter. And there were researchers all across the city and even from outstation who would come, they're punching cards and, you kind of put in the cards, you get out your results and so on. So at least in the next 20 years, I see this happening. Now, beyond that is anybody's guess, right? I mean, Microsoft came along and then everybody had a computer in their house in the late 90s and early 2000s. So this, we don't know where this is going, right? Beyond a point. But definitely we will see these quantum computing facilities.
I'm just going through all my notes I've taken. I'm just thinking that if I have to go deep into this, and if I have to understand this better to prepare myself for the future, because if this is coming in 20 years, I better know something about it. I have to understand qubit, I have to understand entanglement,
Superposition.
the superposition, and entanglement. These are the three basic ideas I have,
Yes,
I have to
indeed.
get.
Yeah, yeah.
Can you give me can you give me a bigger list? So I'm going to make this list. So I must understand what is a qubit. I must understand what is superposition. Third one was entanglement.
Yeah. So from a slightly mathematical perspective, one needs to understand a little bit of linear algebra. So if I want to become a software developer for a quantum computer, right? If I want to program a quantum computer, what do I need to know? So the language or the mathematics of quantum computing or quantum mechanics is all linear algebra. So the better I get at linear algebra, the better I get not just at understanding what's happening, but maybe I can even start coming up with my own new quantum algorithms. I can.
Is this because it's like A first angle, whatever, A theta plus B alpha? I don't know.
Exactly, A0 plus B1, alpha 0 plus beta 1. I had refrained from using things like this, but
Okay.
exactly. It's because it's not just 0 and 1, but it's alpha 0 plus beta 1. And this is an idea of what we call a vector space in linear algebra. So this becomes kind of the basic alphabet in which you talk about qubits and gates and algorithms and all of that. So this language of linear algebra becomes very important. Incidentally, it's also very important in another domain today, namely AI ML.
Yeah.
So in a way, this is a kind of convergence of
Yeah.
new technologies having the same underlying math. I would also say some grounding in probability theory, but maybe that's not as severe a constraint as linear algebra, which I think is absolutely something that people should be super comfortable with if you want to really get into this field.
Makes sense.
On the engineering front, yes, you need to know how to do photonic hardware. Okay, you need to understand. Yeah, I mean, there are certain sort of.
So I don't need to be better at Schrodinger equation. Do I need to?
This is a very tricky question. So it depends on how deep you want to get into quantum computing. Okay, so I want to say that one of the important use cases today, for example, protein folding. How do you solve a protein folding problem on a quantum computer? You use something called a variational quantum algorithm.
Okay.
It's different from Shor's algorithm. It's different from the search algorithm. It's a heuristic algorithm which relies much more on the laws of quantum mechanics and in fact requires some knowledge of Schrodinger, right? So it depends on how deep you want to get into this, right?
Fair enough, but I could choose to, maybe not today, but in 5-10 years, I could choose to, instead of focusing on this, I could choose to become a programmer is there an assembly language equivalent in quantum computing?
It's not a single. So like I said, there are different architectures. In fact, I think we got sidetracked there. So photonics, superconducting, then there are what are called trapped ions and neutral atom based quantum computers. So there are at least these 3-4 different approaches.
So this, you were talking about the architectures of qubit. So
yeah.
photonic,
superconducting,
trapped ions
and neutral atoms.
Okay.
Now, each of these is a different kind of physical object with different kind of control operations for each of them, which are a bit unique. The standard picture you see of a quantum computer is this dangling chandelier, which is actually a dilution refrigerator.
Okay.
That's actually a refrigerator. The chip is somewhere deep inside, and you use this entire array of wires and so on to control the qubits that are lying deep inside. And you're cooling it down to millikelvin temperatures to avoid this decoherence as much as possible and keep them in the state, the superposition state that you want them to be. So this is one example of an architecture, right? Now, IBM has, for example, come up with a Python-based language called Qiskit, right? Using which you can program their quantum computers remotely, right? They have their quantum computers stationed in Yorktown Heights in New York, and you can sort of from here write code and program, access these quantum computers. So it's not still in assembly line language. There are people who have built these full stacks and so on, being agnostic to the architecture. But I think it's still very much a work in progress because in a way, we still don't even know which of these architectures is going to win out. Today, it looks like superconducting qubits are at the lead because they have 100 odd qubits, but neutral atom based systems are also catching up. Trapped ions are catching up. And finally, actually, it would be very ideal if we could do photonics chips, right? Integrated photonics on chip, because those will be your room temperature qubits. You don't need these big chandelier. So a quantum computer occupying like one entire section of this room. But with a photonics-based chip, you could probably have something which is on the table, which is what would be ideal.
So it's a maths, physics, but now as these things get realized more and more, it becomes a heavy
Today, it's very much an engineering problem. Yeah. And I would say what is going to drive the field and what is already driving the field is what one can call quantum engineers, right? Engineers who understand the principle of quantum mechanics and learn sort of how to sort of play around with single quantum systems, right? And engineer, control, design single quantum systems.
That will be very valuable.
Yeah.
If I were JE rank 1, I would probably choose to be a
Absolutely. No, today we see many of the students who graduate from our programs. Actually, there was a time when people who would do engineering, physics and so on would go almost entirely into theory. Now we see more and more of them going into experiments and particularly into quantum hardware. Because I think that's a tool and technique which is going to be useful in the future, no matter, you know, how many quantum computers, facilities we have finally. Right.
Okay. Thank you so much. I have exhausted one set of questions, but I have another 2 sets of questions. So, one line of inquiry that I wanted to talk to you about was there's an India quantum mission.
Yes.
And this is a global player. Every country will try to develop their own resources, and there'll be a little bit of a push and pull on which architectures win or which kind of systems
are going to scale up. Yeah.
So where is India in all this? And honestly, the question is, do we have a chance?
So I actually think that we do have a chance, okay, because the field is still sufficiently nascent. I wouldn't say it's very nascent. I mean, but because, you know, we've had now companies like Google make tremendous progress in the last decade, but it is still reasonably nascent that I think we can still today catch up when it comes to, mainly when it comes to hardware. I would say when it comes to the theory of quantum and so on, I would say we are very well equipped. We are no less than any other country in the world. We have excellent quantum information, quantum computing theory groups across the country. Experimentally, over the last decade, we have definitely made efforts to strengthen our experimental efforts. So we have the group at IIT Madras led by Prasanil Prabhakar, who works on building quantum communication hardware, which is an aspect which I've completely not touched upon at all. Maybe just a word or two, since we are also a quantum communication hub under the National Quantum Mission. What is the idea here? The idea is, okay, now you say quantum computers are going to break classical crypto systems or your the things like RSA. But can you now replace these classical security systems with quantum secure systems? And here again, quantum mechanics comes to the rescue. So there's a way to do the same public key distribution that RSA does using quantum states.
Okay.
So now instead of sending your info, now like how we spoke about computing with quantum states, you now think about your information carriers themselves as quantum states. Again, not too hard because, you know, photons are traveling objects and you can send them from place A to place B. And here entanglement also plays a crucial role. So there is a protocol called quantum key distribution, which allows you to distribute key over public channels in a way that is quantum resilient or quantum secure. So even if you had a quantum computer, so the security of these kind of quantum schemes relies on the physics properties of these systems rather than on the computational hardness of a mathematical problem. So why RSA became vulnerable is because it was a problem which was hard classically but not hard quantumly. Now you are kind of not even having computational assumptions, but you're having physical assumptions like quantum mechanics is valid. The uncertainty principle is valid. So
Professor Anil's group, sorry, what is it called?
It's called quantum key distribution.
So what is Professor Anil's group called?
So we call ourselves a Center for Quantum Information, Communication and Computing, CQUIC. Okay. And we are one of the hubs under the National Quantum Mission. So they made 4 hubs. One for quantum communication, which is with IIT Madras. One for quantum computing, which is with the Indian Institute of Science in Bangalore. One for quantum sensing, which is again another domain which I've completely not touched upon, which is in IIT Bombay. And a 4th one for quantum materials at IIT Delhi. So these are the 4 verticals which the government is focusing on, and most governments across the world are kind of focusing on these. And these form the pillars of the field, so to speak. So quantum communication, we have Professor Anil's group here. We have Professor Urvashi Sinha's group at Raman Research Institute, who has been doing, again, fantastic work in quantum key distribution. They are trying to do satellite-based quantum key distribution. We have Bhaskar Kanseri's group at IIT Delhi. So we have a few different groups on quantum communication. We have a few different groups that are building quantum hardware, like Professor Vijay Raghavan's group at TIFR, Professor Umakant's group at IISER Pune. And again, the government has wisely distributed money across different architectures so that you're not putting all your eggs in the same basket. You're funding superconducting qubits, you're funding trapped ions, you're also funding photonic-based groups in Indian Institute of Science, Professor Chandrasekhar's group. You're also funding trapped ions, that's IISER Pune, Umakant. So the National Quantum Mission, I think, has kind of done a fair job of assessing the key groups, technical areas in which, we need funding.
I'm a little confused on one thing. What would the National Quantum Mission, because it's such a nascent field, right? So what is the goal? What would we achieve?
Yeah, so the goal for the communication hub, for example, is to build a quantum secure route, let's say between Chennai to Bangalore, for starters. Can you set up a quantum secure link, communication link between Chennai and Bangalore?
So quantum encrypted here, quantum decrypted there.
Exactly. Yeah.
Okay.
Now, with present day research and technology, this will not happen with a single link. It will require a few hops in between. Those hops will have to be trusted nodes, right? And this can be done. Now, this is not, okay, so China demonstrated this a few years ago, where they showed such a quantum secure link from Beijing to Shanghai, which is, of course, much longer. So one of the mission goals, some more ambitious goal, is can you now do this from Chennai to Delhi? Instead of Chennai to Bangalore. But we're starting with Chennai to Bangalore. So IIT Madras, for example, we have now set up a quantum secure link from IIT Madras, our lab in the electrical engineering department here, to the research park. Right?
Okay.
This is one such point-to-point link. But now you want to sort of stretch this and make it across cities, intercity, and so take it all the way to Delhi, for example, is one of the goals of the National Quantum Mission.
Okay.
Right? For computing, the goal would be, can you build a chip with, let's say, 50 qubits? And you wouldn't be too far behind. I mean, IBM may have 100, 150, but if you have the technology to build and control 50 qubits, then you're not too far off from sort of realizing that. So that's another goal of the National Quantum Mission.
Okay.
So these are the kind of goals that have been set, very targeted, very concrete goals. And teams have been identified to work towards these specific objectives.
Yeah. Okay. And this is like it's an engineering challenge, photonics challenge, electrical engineering challenge, and a physics problem.
Yes, absolutely.
These are the fields that are intersecting.
Right. Well, also computer science from the perspective of, can you come up with new algorithms?
Okay.
Right? Can you optimize even the existing algorithms so that if you have noisy devices, then, can you do some special tricks that can push you faster, towards a solution and so on. So it's I would say, a confluence of mainly computer science, physics, math, electrical engineering, right? But now I would say we also have chemists and biotechnology people in the mix, because the kind of problems we are going to solve finally, which are going to have lasting impact, will be the problems of drug delivery, drug design, protein folding, and so on and so forth. So which needs domain knowledge in chemistry, which needs domain knowledge in biosciences.
Yeah.
So it's kind of an interesting melting pot.
Wow, it's amazing.
So I should mention that our center itself has faculty from all these disciplines that I just mentioned. We also now have faculty from management sciences, because operations research folks are very interested in quantum computing. Because you can solve all these different optimization problems, bin packing,
No, for sure. Operations research as a field started because they wanted to, because the Americans wanted to distribute their supplies across the war front in World War II.
Yeah.
It's a computation challenge more than anything else.
So, for example, the center has industry collaborators. So, one of our biggest sponsors is Emphasis Foundation, right? Okay. And what are they interested in mainly is an entire suite of these kind of optimization problems, right? For example, EV charging electric vehicles, right? So, you have some configuration in your grid, so to speak. Now, what is the optimal sort of solution for this? This could be something that can be cast as a quantum problem and run on a quantum computer, right? We have companies like Boeing and Airbus being interested in quantum computing. We have companies like Siemens and Bosch being interested. So it's kind of Mercedes.
The
Right.
EV charging problem is, how do I use my existing grid to charge so many electric vehicles at so many points,
Correct.
at what time
Yeah.
of the day, at
Exactly.
what
Yeah.
current, and not
Right.
completely destroy the
Correct. So you want to
existing-
optimize, you want to optimize power. So you can identify the cost function that you want to optimize, right? And you can cast it into a quantum problem.
Professor, one area of inquiry that I have is, I mean, how did you get into this? What is your personal journey?
Yeah. So I did a bachelor's in physics from Chennai, Ethiraj College in Chennai. And then I came to do a master's in physics in IIT Madras. So full disclosure, my father himself is a theoretical physicist,
Okay.
now retired from University of Madras. And he worked on an area called quantum foundations.
Okay.
Okay. Or the theory of quantum measurement, which was at that point considered very esoteric sort of thing. He was trying to really understand the nitty-gritties of quantum measurement and so on. Interestingly, his papers are now very well cited today because, quantum measurement has become such an important problem because of quantum technology, right? So in a way, the seeds were probably sown by some discussions with him. But really, after I joined my master's here at IIT Madras, and we did our first quantum mechanics course, and we were all asked to give presentations on some topics. And I think I chose something called this Bell experiment, Bell CHSH experiment, which actually won the physics Nobel 3 years back. And I think in reading about that, in even talking about it, I was really excited. Somehow something clicked. And then I went on to do my master's project under Professor Arul Lakshmi Narayan. We studied early papers on quantum entanglement, and I ended up working with him on something called quantum random walks,
Okay.
which is again different from a classical walk, and it's again some interesting stuff there. So all of this, I think, kind of propelled me in this direction. So I realized that I really like the math of quantum mechanics, and then I really liked the idea of entanglement, the idea of doing tasks like random walks with quantum particles and stuff like that. I got introduced to a book by Nielsen and Chuang, which had just come out. And then I applied for grad school and got into one of the, at that point and even today, leading groups on quantum computing with Professor John Preskill at Caltech. So I think that kind of cemented the deal.
I want to ask you a question here. I understand that you were exposed to it early,
Yeah.
which is amazing. But still, at the time you're talking about 2003, 2005, it's a very esoteric field.
Yes.
You're committing your career to it.
Right.
Isn't that like a nerve-wracking decision that, am I going to do this? What if the field doesn't move for 30, 40 years?
So I should tell you that I was one of those people in 2000 who actually did not write the JEE exam.
Okay.
So I knew that I wanted to do physics for whatever reason. And at that point, maybe the only option was to go for an integrated physics program in IIT Kanpur. And then there was all this conversation at home, everyone in class was going for JEE coaching. In Chennai, you're also a Chennai person, so there were specific classes that you would go to for JEE. I didn't go because I spoke to my dad and he said, do you want to do engineering? I said, no, I don't want to do engineering. Then he said, why are you writing the JEE exam? So I said, okay, maybe I don't need to write the JEE exam. So, I have never thought about this as, is there a, career path here? It's more about what has interested me. I've been lucky enough to kind of follow my interests that way, right? But I have always done that. And maybe that's why I did not think too much. For example, even in theoretical physics, most of my peers were applying, when they applied for PhD, whether abroad or here, were applying in string theory. It was still the heydays of string theory, right? And everyone either wanted to do particle physics, high energy physics, CERN, or string theory. But to me, what was fascinating was quantum information and entanglement and all of that. So in a way, I was bucking the trend, even in theoretical physics. It's true that I'm one of the earliest probably who actually went on to do a PhD in quantum computing. So yeah, but well, it worked.
It worked out. I would summarize that you had not only early exposure, you had a very supportive parent.
Absolutely. No, absolutely. Yeah. No, my parents were very supportive.
Who didn't push you down JEE path?
Not at all. No, very, very supportive. Yeah.
Amazing. So you mentioned that you were a master's student here at IIT Madras. I think that's 2003 to 5.
Yep.
What was the department like then, and has it changed a lot from then to now?
Also,
And I also want to give you what I have heard from
Mhm.
aspirants.
Mhm.
Obviously, in 11th and 12th, lot of students do want to do physics.
Yeah.
They are unable
Yeah.
to do because there's a lot of peer pressure.
Yeah.
But when they
Yeah.
want to do physics, they
Yeah.
kind of look at IIT Madras as a place they would want to come to.
Yeah, no, I think today, I mean, this might not have been the case maybe 20 years ago. First of all, 20 years ago, we barely had started the engineering physics program, right? I myself was a master's in physics. Like I said, you see, if I was a class 11, class 12 person who wanted to do physics or even mathematics for that matter, or chemistry, where are the institutes where I could? This was before all the ICERs came up. There were very few options to do an undergraduate physics program. I think IIT Bombay had an engineering physics program already. By then, IIT Madras still did not have. When I started my BSc, for example, IIT Madras did not have an engineering physics program, right? It started, in fact, in 2003, if I'm not mistaken, or 2002. So the first batch of engineering physics students graduated in 2006 from IIT Madras. So it was a much smaller department then, right? Mainly, we had masters and PhD students, right? And even those numbers were fewer, right? And the undergraduates who came in to attend these physics courses were like the really motivated, interested people who really wanted to do physics, despite having been pushed into JEE and pushed into taking one of these branches. But then the love for physics superseded all of that, and they came and did physics courses. But I think today, well, of course, the subject has grown, but also the department has grown tremendously. Back then, the theoretical physics group was very small, maybe 5, 6 faculty. Today, we have maybe 15, 16 faculty, and we are still growing. The experimental group was mostly low temperature physics. Today, we have again grown much bigger than that. We have people who do optics, ultra fast lasers, we have photonics, we now have people who have tie-ups with all these big experiments that are running worldwide, like CERN, the particle physics experiments. We have a very active particle physics group. We have a very active cosmology, general relativity, gravitational wave, group. So I think we have really expanded on all fronts. And of course, we have an active quantum computing, quantum information group, even within physics. Almost all of us are part of the center that I described. So I think the department has grown tremendously. We now have a dual degree physics program. The engineering physics program now, I'm told, is ranked higher than
In the other IITs.
Yes. And in fact, I'm told that our closing rank this year in counseling was even better was next only to computer science and EE. Which is, I think, a big achievement. But I think it grows to show that the program itself, I would say, I mean, I've taught EP students since so I joined the department back about 10 years ago. And I've taught a few batches of dual degree physics and engineering physics students, very motivated kids. And I think since, we now have several young faculty in the department, dynamic faculty. So there's something very, I think there's a lot of action happening on the physics front. And so the students are picking up on it, and we get some very good students today.
Yeah, the movement in the ranks for EP has been quite incredible.
Right. And I feel that engineering physics students, at least from a quantum perspective, are the best placed to enter a field like quantum science and technology, because you come with some amount of electrical engineering knowledge, which as an MSc physics person, frankly, I don't, right? I had to pick up several things along the way. Even my knowledge of computer science or something is very picked up later, right? I, in fact, attended an information theory course during my grad school just to pick up on classical coding, classical information, and all these ideas. But someone who's doing an engineering physics degree will naturally have those courses. They will have quantum mechanics. So it's very easy to, I think, get into this field today if you're an engineering physics graduate. Yeah.
Nice. Thank you so much for all of that. I've already occupied your time a lot, so I will let you go. But one last question I want to ask you. There are a lot of women students taking these courses. And I'm asking you because I came from mechanical engineering and my class had maybe a 10%. Uh, uh, Even today, we get questions from parents saying, is this suitable for, I don't know why. I don't know why. What do they think that engineers do But they still ask us questions like, oh, is naval suitable? Is chemical suitable? I don't know. But I would ask you that question. Is this a field that sees a lot of women in it?
At the moment, not yet, right?
Yeah.
Our ratios unfortunately haven't changed much from the 10% that you saw, right? In engineering physics, I think in a batch of about 40, 45, maybe we have 10 girls typically.
Okay, so that's
That's
20,
a little bit better,
yeah,
right? It's 20% almost, I think, which is good. And I think also initiatives like the supernumerary, sort of
supernumerary fields.
yeah, I think that helps, right? Certainly. So I think, to me, the biggest problem for women in STEM fields is that at some point, I mean, I would say by and large, Indian parents, we are very supportive of women's education, I must say, in general, right, as a society. Because I don't believe that, I don't buy this thing that we are very conservative. We are not at all conservative when it comes to educating our women, right?
I mean, there's data on this because in CBSE, women outperform men all the time.
Absolutely, absolutely. Yeah. I mean, my son is in class 4, and I can tell you that the number of girls in his class is, first of all, outnumbers the number of boys, and the number of top rankers who are girls is much higher, right? So, this is very true. But I think what happens is, after a certain age, society starts imposing certain, um, not constraints, but more like expectations, that now you need to do this, this, and this, right? And then this, and this come with all these constraints. But then you start second guessing yourself. You start saying, should I really go for that master's, which is going to take me 2 more years? And then what do I do? And then should I really go for this PhD, which is like 5 years long?
Interesting.
You know, or should I, at this point, I'm getting placed, let me take this job. I mean, nothing wrong in that, but I'm just saying that the choices that girls start making at 2021 is, I think, what pushes down the number of women who are, sort of, see, you need that extra qualification, you need that extra skilling, right, in order to be able to enter a niche area like this.
Yeah. Also, there are some fields, I feel, there are some fields, if a woman in 11, 12 or 8, 9, 11, 12 has decided that I want to have a long career, there are some fields which are predominantly women. Like I come from marketing, there's a lot of women in it.
Right.
So by default, they choose fields where there are more women. So I think in these.
But that, I think, is just a peer thing, I think, it's just because I don't see a marketing job as being any less stressful or any less demanding than, let's say, the job that I do, or the job that, let's say, a quantum engineer in Google will do.
Yeah, I don't mean in terms of easy or hard. I mean in terms of, say, for easier choice.
Yeah, but I'm saying that is just pure peer-driven.
Okay, fair.
Right? It's like, for example, okay, so I went to do a PhD.
It's not a really logic-driven.
I don't think it's very logical. Because if you really think about how time demanding it is and so on, it's not any less demanding, right? Because I see, women, I have friends, women who are in marketing, they're all the time having to, you could have client calls in the middle of the night, you could have client calls early in the morning.
Yeah.
Whereas if you think about it, I actually do not have calls in the middle of the night. I set my calendar myself, frankly, if you think about it. So in a way, I find I have more freedom sometimes. So I think that's not so logical in a choice. But I do think that there are more women there, so women kind of tend to. So like when I walked into my advisors group meeting for the first time, there was only one other woman in that room with maybe 20 men. This was not even the case in my master's class in IIT Madras. We were 10 girls among 40, which is a reasonable number, among 40, 45, class of 40, 45, there were 10 of us girls. So this PhD actually was the first time when I was in a group which was entirely male dominated. There's one other female graduate student. At any given point of time, we would have a group of 15, 16, which is one or two women, either one woman postdoc, one woman PhD student. So I think that maybe daunts us sometimes, right? And so we say, oh, but there are no women there. So why should I be really there? But I think we are second guessing ourselves in asking these questions. So what?
Yeah.
What does it matter? So long as your colleagues treat you in a fair way and there's no, and I don't think I faced any, frankly, no such, I never felt like, oh my God, I'm squirming because, No, no one. So I think so long as everyone's respectful and treating you like, anybody else in the room, there's no issue.
Yeah, and this is a field where your gender really doesn't give you an edge for anything. You could be a man or a woman.
Absolutely, absolutely. I do think that the main issue that happens is After a certain age, you maybe have additional constraints, additional responsibilities. But today, in today's day and age, we have developed mechanisms,
To work.
to work with it. So I see no, barrier as such.
Thank you so much, Professor. That was a long conversation, and
Thank you. I hope I did not bore everyone with all my quantum. I get into teacher mode very easily. So
we will in the YouTube description we have left links on some of these things, including the links to her NPTEL courses, so you can check them out. Professor, any final thoughts before we close?
well, I would just say if you are a high school student or even an undergraduate watching this podcast, uh, the next decade, I think, is a very exciting time for quantum science and technologies. I think it is a good time to get into the field where you get to learn a lot of new things. You get to be a part of exciting new developments that are happening around. And no matter which course eventually history will take, I think you end up learning some very nice skills which will last you throughout. So that's my,
Thank you, Professor. Thank you, everyone, for listening in. Please share, subscribe, send this podcast as a link on WhatsApp to your friends. Thank you.